Hello, everyone. We are now beginning chapter 11, which is the last chapter of the book. But we're still only maybe a bit more than halfway done now. There's a lot of sections. There's 11 sections in chapter 11, and we're going to cover, maybe one is a review section. So there's, a lot of sections left. But we are in the last chapter. So, uh, some notes about this chapter. It's kind of separate from everything we've done so far. Okay, so maybe if you're feeling a little behind on the material and you feel like you're playing catch up, this is kind of a good place to jump back on. It's kind of a fresh starting point for everybody. So this stuff is, like I say, not. We're going to see some connections to the previous material, but it's kind of its own thing. And I think it's a really important topic. We're going to be covering sequences and series. And after you get done and go on to other subjects, maybe you'll say to yourselves, oh, why did we even bother learning that? But looking back on it with a bit more perspective than maybe you guys have, this material is some of the most important material in the calculus classes, Calc 1, 2, and 3. This is material I use on a day-to-day basis, doing my studies and my work. It's very technical, but it's got a lot of theoretical applications, and it's got some practical applications as well for you engineering and computer science people, or whoever else we have in our class. Okay, there are a lot of practical applications to this stuff. But let's start with some theory. 11.1 is all about sequences. Okay, so what is a sequence? A sequence is just an ordered list of numbers. Okay, so what do I mean by ordered list? Okay, we could have a sequence like this, where we have our numbers 1, 1, 2, 3, 5, 8, and so on. And this dot, dot, dot means, this ellipsis means we're going on forever. So we're studying infinite sequences, sequences that go on forever. Okay. And how is this series ordered? Well, by order, we mean the order our numbers appear in. Okay. So this one here, that's the first term of our sequence. This is the second term of our sequence, third term, and so on. It's pretty obvious what I mean. Okay. But these terms might not be in numerical order, right? We might have a sequence like, oh, I think I had an example actually. Yeah. So we might have a sequence like this. This is clearly not numerical order, right? But this is still the first term of our sequence. This is still the second term and third term and so on. Okay. So by order, we just mean the order our numbers appear in. Okay. There might be some rule that kind of governs, how our sequence looks, maybe not. So these three things are all ways to kind of write a general sequence. Like if I want to write out, if I want to use some notation to say I'm dealing with a sequence, but maybe I don't want to list all the numbers. Okay, what could I do? Okay, I could have a couple things. Actually, let's go back here. I could just write out braces. These curly brackets are called braces. Okay, I could just write A1, A2, A3. These terms are all separated by commas, and then okay, I have an ellipsis here. That means my sequence goes on forever. So that's one way to write a sequence, and just to kind of denote I'm dealing with a sequence. Another way is to put braces and then just have an AN in the center. Okay, AN in the braces. And the N, using N, that's kind of standard, but it's not necessary. We could just as easily use like AK or AI, something like that. Usually some letter. Usually we have a letter here that's our kind of our number, and then this number here is denoting the order our numbers appear in. And then outside the braces, we have n equals 1, meaning we're starting at 1. And then we have infinity up here, meaning we're going to infinity. Okay. And then the third way is maybe similar to this, but we just drop the n equals 1 and the n equals 1 in the infinity. And we just write braces with an in the center. That's another way to denote a sequence. Okay. Out of these, I like this second one the best. This is one I tend to use. Okay. It doesn't really matter though. So these sequences, how are they formed? What do they look like, and etc. Sometimes there's going to be some rule or formula that tells us what the terms of our sequence are, and sometimes it's going to be seem totally random. Okay, so an example would be, let's say we're given this rule. Okay, so let's work on this example. Let's say we're told that an, my term of my, this would be, what does an mean? Okay, an is the nth term of our sequence. Okay, so if I have like a5, that's the fifth term of our sequence, right? So this formula is a general formula for all the entries of my sequence. I'm told that an equals 3 to the power n over 1 plus n. Okay, so let's first figure out a couple terms, and then we can deal with this. We can write this sequence somehow. So what happens if, what is a1? Okay, what is the first term of my sequence? I'm going to take the number 1 and plug it into this formula. And what do I get? I get 3 over 2. Okay. Now I'm going to take 2 and plug it into my formula. And what do I get? I get 9 over 3, and so on. So these are the terms of my sequence. So my sequence might look like this. Okay, I've written out the first few terms here, and then inside my braces, and then I have my ellipsis, meaning it goes on forever. Okay. Or what's another way to write this? I just write the formula in the center of my braces, and then I use that notation from n equals 1 to infinity. I could also do, that third way of writing out my sequence, 3 to the n over 1 plus n, just in braces. Now, sometimes there's a nice direct formula like what we saw here, right? The good thing about this formula is I can figure out what any term of my sequence is. Let's say, they give me this formula, and then someone comes along and says, hey, what's the 100th term of your sequence? How do I figure that out? Well, I just plug the number 100 into this formula, right? So I kind of think of, I'm not sure if it has a name, but I think of it as a direct formula for our sequence. But other times we're going to be given something called a recursive formula, and this is a this is a known quantity. This is the actual terminology people use for this. A recursive formula for the nth term of our sequence. Okay, so what is a recursive term? It means our nth term is the only way we can figure it out is, or maybe the way we figure it out at first, is going to be in relation to the previous terms. Okay, what do I mean by that? Let's consider the Fibonacci sequence. If you guys have ever heard of the Fibonacci sequence, what does the Fibonacci sequence look like? I actually wrote it out earlier. This here is the Fibonacci sequence. How is the Fibonacci sequence formed? Okay, we're going to start, I'll go to a new page. We're going to start with, we'll say the first term of our sequence is 1. And we'll say the second term of our sequence is also 1. And then from there on, an is going to be the sum, my nth term is going to be the sum of my 2 previous terms. So an is going to be a n minus 1 plus a n minus 2. Okay, so that's like, this is a recursive formula for my sequence. So let's say I wanted to find out the next several terms. What would a3 be? Well, I don't have a formula that tells me what a3 is directly, right? There's no like nice formula like 1 over n plus 5, and I just plug the number 3 into this and I get my term. To figure out what a3 is, I need to know what a2 are, what a2 is, and what a1 is. Okay. in this case, I do, right? I do know. So I know A1 is 1, A2 is 1. So that means A3 is going to be 1 plus 1, which is equal to 2. What about A4? Okay, well, that's going to be 2 plus 1. Okay. So A4 is going to be 3. What would A5 be? Well, that's going to be 3 plus 2, which is 5. Let's do one more, A6. Well, that's going to be 5 plus 3, which is 8. Okay. So far it seems like I'm figuring out these terms very easily. But now let's try and skip a few. What if they ask what A15 is? Okay. And this is the only information I know, right? I know A15 is going to be A14 plus A13. But I don't know what A14 and A13 are, right? So to figure out what A15 is, I would have to like work my way up from the beginning. I'd have to find what A7 is, A8, etc., all the way up to A13, A14. And then once I know all this, then I could find A15. Okay, so that's what a recursive formula is. It means like we can't just jump in the middle. I can't just find, my 100th term and my 1000th term. I really have to know all my terms before that as well. The recursive stuff may or may not come up in your homework. I don't believe so. I just wanted to give that to you for completeness. The first type of problem we're going to see is kind of working backwards. I kind of said, all right, there's a formula. Maybe there's a formula for the terms of my sequence. Okay, so before we saw the formula 3 to the power n over 1 plus n, something like that. Okay, and then we kind of wrote out terms of a sequence, right? The first problem we're going to see is we're actually probably going to work backwards. We're actually probably going to be given several terms of our sequence, and we're going to be asked to find a formula. Okay. So how do we do that? Well, it's essentially pattern recognition. We want to be able to recognize these patterns. And there's there's the problems you're going to see have a lot of common patterns. They're usually going to be powers or sums or factorials. I won't cover factorials today. These are going to be more important in later sections. And then if we have a sequence where we have fractions, where I have like numerator and denominator, I'm usually going to look at the numerator and denominator separately, okay, and look for patterns in each. And then if there's alternating signs, meaning maybe my terms of my sequence alternate between positive and negative, okay, that's another common pattern. Okay, so I've just stated a bunch of patterns here. This might make more sense in retrospect, but I'll kind of try and give you guys some tools to find these patterns. So let's see an example first. Let's deal with this one. I have 1 over 2, 1 over 4, 1 over 6, 1 over 8, 1 over 10, etc. And maybe you guys can already spot the pattern here. Okay. What's going on? Well, the numerator is always 1, and then the denominator is just going 2, 4, 6, 8, 10. I would expect the next one to be 12, and then 14, 16, so on. Okay. So kind of clear what's going on. How can I write this in general? All right. Well, I need a formula for an, where an is just some general n. Maybe I want to plug 100 into there, 1,000, etc. I need a formula that works for any n. Okay. Well, what's going on in my numerators? This is kind of the thought process I go through when I'm finding these formulas. All my numerators are 1. Okay. So I kind of expect that the numerator of my general term an is going to be 1. And then what's going on here? I have even numbers, right? Well, how can I write even numbers? the first tip I'll give you, all the even numbers, whenever we have an even number, we can write them as like 2 times k or something like that, where k is some integer. And then odd numbers, we always write as like 2 times k plus 1. I could use n here as well. So even numbers have this form, odd numbers have this form. Okay. So it looks like my denominator is going to be 2 times n. Okay. So let's just double check. We've kind of have this formula that we kind of suspect is our correct formula. Let's double check. How do we double check? I'm going to plug in, let's see, this is the first term of my sequence, right? So I should be able to plug 1 into this formula and get this number 1/2. Okay, does that work? Okay, I plug 1 into my formula and I get 1 over 2 times 1. That's 1/2. Good. All right, that matches. I plug in 2 and I get 1 over 2 times 2. That's 1 over 4. If I plug in 3, I'm going to get 1 over 6, etc. So that matches. So yeah, it looks like my formula is an is equal to 1 over 2 times n. Similarly, if I had been given this sequence, 1 over, let's see, about 3, 1 over 5, 1 over 7, 1 over 9, etc. This is all the odd numbers in the denominator, right? So I want to write out a formula for my an. Well, my numerator, I got a fraction. I always have a fraction. The numerator is always 1. What's going on with the denominator? It's an odd number, which I should usually write like 2n plus 1. And then I just double check. Okay, so I plug in 1, and what do I get? I plug 1 into this, I get 1 over 2 times 1 plus 1, which is 1 over 3. Plug in 2, I get 1 over 5, and so on. So it's checking out. Let's move on to this slightly more complicated example. So let's say I have this sequence here: 4, -1, 1/4, -1 over 16, 1 over 64, and so on. Okay. So this pattern maybe is a bit harder to work with. Okay, I know something's going on with 4s, right? I got 4, I got 1 over 4, 1 over 16, etc. What's the exact formula? Okay. Also note that I have an alternating sign. Okay, got a positive here, negative, positive, negative, positive. Let's deal with this piece by piece. Okay, usually when we're trying to find these patterns, we can deal with kind of each component separately. So let's first deal with the alternating sign. I have a positive number here. Okay. Okay, so I can think of this 4 as 1 times 4, right? And then I have a negative here. So think of that as like -1 times 1. Okay, maybe it's kind of unclear why I did this. You'll see in a second. Okay, then I have 1 over 4. Okay, so I can think of that as +1 times 1 over 4. Then I have -1 over 16. I can think of that as -1 times 1 over 16. Okay, and so on. All right, and now think of this stuff. Let's think of this stuff in parentheses first. I got +1, -1, +1, -1. Well, I know positive. Let's see. How about +1 is the same thing as -1 squared. And then I got -1, which is the same thing as -1 cubed. And I have +1, which I could think of as positive 1, or excuse me, negative 1 to the power 4. And then I have negative 1, which I can think of as negative 1 to the power 5, and so on. Okay. What I'm trying to show is that this alternating sign, these alternating signs can always be written as negative 1 to the power n, or negative 1 to the power n plus 1. Okay. And there's a difference here. Let's say I have a sequence that goes like positive 2, negative 4, positive 6, negative 8. Okay, so it's starting on a positive. All right. I'm going to use, let's see, I would use this form. Why? Because when I plug 1 into this, okay, when I plug 1 into this, my first term is going to be positive, right? I'm going to have negative 1 to the power 1 plus 1, which is negative 1 to the power 2. So when I plug 1 into this formula, my first term is going to be positive. Okay. On the other hand, if I plugged 1 into this, I would have negative 1 to the power 1, so my first term would be negative. Okay. So the short story is when we have these alternating signs, so when we have alternating signs, when I see positive, negative, or negative, positive, that's either going to be negative 1 to the power n or negative 1 to the power n plus 1. Okay. And we just need to make sure our form matches with what we're seeing. All right. Meaning, okay, in this case, we're starting with a positive number. So I'm probably going to use this one. Okay. So I know my formula for my terms is going to involve this negative 1 to the power n plus 1. Okay, so that takes care of my alternating sign. Okay, so now I can just ignore the alternating sign and just figure out, I can just look at the numerical values. I got 4, 1, 1/4, 1/16, so on. Okay. Maybe the pattern isn't clear for these first two, but then starting here at 1/4, what do I have? I got a fraction, and I got 1/4. Then I got 1/16, which is really just 1/4 squared, right? And then 1/64, that's 4 cubed. Okay. All right, how could I think of 1? Remember, we've already taken care of the alternating sign, so ignore negative 1, ignore the negative sign, and just focus on that 1. How could I write 1 in terms of these powers? Well, 1 I could write as 1/4 to the power 0, right? 4 to the power 0 is just 1, so I'd have 1/1, which is 1. And then what about this 4 here? I could write that as 4 to the power 1, right? Or I could also write that as 1/4 to the power -1. Those would both give me 4. Okay. So I have a little bit of a choice here. I could, using this stuff, I could write my formula as, let's see, 1/4 to the -2 plus n. How about that? Okay. If I plug 1 into this, I would get, let's see, let's assume this is my formula. Let's see if it works. Let's plug in the number 1, and what do I get? I'll get -1 to the 1 plus 1, okay, times 1/4 to the -2 plus 1. Simplifying, okay, that'd be positive, then 1/4 to the -1, which is 4. So that matches up with my sequence. I get a positive 4. If I plugged in 2, I'd get -1, which matches with what I want, okay, and so on. So it looks like my formula is correct. But as you might have guessed, this is just one way to write it. There's, maybe a couple ways to write this formula. First of all, this 1 over 4 to the negative 2 plus n, I could have also written that as 1 over 4 to the n minus 2, right? Same thing. I could also write this as 4 to the 2 minus n, okay? Same thing. And there's probably a couple other ways I could write this. So all these three formulas give the same thing. Okay. And really, I mean, they're just kind of rearrangements of each other. Okay. So if you do it one way and your friend does it another way, okay, that's, you know, that doesn't necessarily mean one of you is wrong. All right. So that's kind of our first problem of this section, trying to find these formulas for our sequences. Now let's discuss ways to visualize these sequences. And I'll do a lot more examples of finding these. This is kind of it's kind of a tricky thing. It takes a little bit of practice. So this will be covered more in the problem video. Now let's move on to ways to visualize these sequences. Okay. So there's two kind of methods. This first method I don't use very much. We could think of these entries, these terms of our sequence. We could think of those as dots on our number line. Okay. So let's say I just have a flat number line, and let's put these terms on our number line. Well, the first term, A1, was just 1, so that'd be there, right? And then A2, okay, that'd be at 1/2, which is about there. A3 is at 1/3, which we'll call there. Okay, then 1/4, 1/5, 1/6, 1/7, and so on. And so I can picture these as dots going here, right? So that's one way to picture these sequences. And this graphical stuff, it gives good insight into what's going on. Looking at this graph here, this number line, I can tell what my points are doing, right? I'm starting at 1, and then I'm getting closer and closer to 0, and they're getting closer and closer together. So that's an important insight we're getting from this number line. We could also graph these as a function, and you might be asking, okay, what's this n here? Well, this kind of bold n stands for the natural numbers, which are our positive integers, right? Like starting at 1, 1, 2, 3, 4, 5, and so on. Those are our natural numbers. Okay. So I'm used to graphing functions of the real numbers, like the whole number line, okay, which would look like something like this. Okay. But these sequences we can think of as functions of the natural numbers, meaning, okay, at point 1, I graph A1. So maybe A1, let's use this sequence again. So at this x value 1, I plot A1, which is, I'll do it in blue again. A1 is 1. And then at 2, I graph A2, okay? A2 is 1/2. And then at 3, I graph A3, which is 1/3. And then A4 is 1/4. Okay. And then I continue going on. And this gives similar insight, right? I would graph a bunch of points like this, and I can see what my points are doing. You know, I can, my points as n increases, as I increase my index, my points are getting closer and closer to 0. Okay. And this kind of way of thinking of these sequences as functions, this is what I do, and this is kind of the way I'll draw these throughout the section. Okay. So this is really just preliminary stuff. It's kind of this stuff of being able to make a formula and being able to kind of draw these sequences and or plot them and giving this graphical representation. These are just handy ways to think of our sequences. What we are usually concerned with for sequences are limits, okay? So this is the majority of this section of the book, 11.1. It's the limits of sequences. Okay. So what is the limit of, we've dealt with limits before. What are we talking about when we're talking about the limit of a sequence? It's really the long-term behavior, right? What's happening to this sequence as n goes to infinity, as we go further and further to the right? Well, my points are getting smaller and smaller and smaller. And that's just for this sequence, right? So for other sequences, I want to figure out similar stuff. I want to figure out the long-term behavior, this long-run behavior as n goes to infinity. In other words, we want to figure out what the limit of our sequence is. Okay, that's the intuitive idea of the limit. It's that long-term behavior. So let's revisit the idea of the limit real quick. We got the intuitive idea, but let's talk about the rigorous mathematical definition. And this is a little bit of a taste of kind of the mathematical formalism you would encounter if you went further in math. So I'm going to give a very technical definition of a limit, and then I'm going to discuss what it means. Okay. So let's let L be a finite number. Okay. And let's consider the sequence AN. Okay. We say that the sequence AN has a limit L if for every epsilon, this is the Greek letter epsilon, okay, for every epsilon greater than 0, there's an integer n such that a of n, the absolute value of a of n minus L, is less than epsilon for n greater than or equal to n, big N. In that case, we say that the limit of an as n goes to infinity equals L, and this is the notation for that, lim an equals L, or an to, the arrows to an to L as n to infinity. Okay. So this is a very technical definition. Let's kind of dissect what it means. We have some number L, okay, just some finite number, and then we have this sequence an. When is the limit of our sequence equal to L? Okay, let's pick some number epsilon. Okay, so this Greek letter epsilon stands for any super small number you could possibly think of. Epsilon could be 1 over a billion, 1 over a trillion, so on. Okay, so epsilon just kind of stands for any arbitrarily small number. Okay, so we say that the limit of an is equal to L if for every small number epsilon, the distance between an and L is eventually less than epsilon. So again, maybe that's not very clear. This is where the graph comes in. These graphs of our sequences. Let's consider this sequence here, 1 plus 1 over n. Okay. Well, what does our sequence look like? Well, my first term would actually be 2, right? So let's put 2 up here. First term would be 2. Okay, let's say this is 1, 2, 3. I know my scale's all messed up here, but these values get, it's hard to see the difference if I don't kind of scale things up a bit. So my first point is at 2. Where my second point be? That would be at 1 plus 1/2, or 3 over 2. And then 1 plus 1/3. Then 1 plus 1/4. 1 plus 1/5. 1 plus 1/6. 7th. And so on. Okay, so if I continue this trend, we see that as we move to the right, my points are getting closer and closer to this dotted line, right? Which is just the value 1. Okay. So my points are getting closer and closer to 1. What do I mean by getting closer and closer? Well, I could for any kind of border around this white dotted line. Let's say I draw this kind of green border here, right, on both sides of my white line. Eventually, my sequence is trapped inside that border. Okay. And what is the width of this border, or what's the kind of radius of this border, this zone? Well, that's my number epsilon. This is just some arbitrarily small distance, right? And I could repeat that process for any epsilon. Okay, so I've done it for this green here. Okay, let's say this green distance from this distance here, this radius, let's say that's 1 over 100. I could repeat the process for 1 over 200. Let's call that this yellow line. I got this like little yellow border here that's really close to my white line. Okay, and maybe you're able to tell, but eventually and the scale's all messed up on this, but eventually my points are going to be within that yellow border of this line. Okay, so that's what we mean with when we say, okay, this distance is going to be less than epsilon for n greater than n, right? For this yellow border, there's some integer n way down the road where eventually for all the points after this n, my sequence is within my yellow border. So that's the formal idea. This is not going to come up too much, but it's in the textbook, and it's this kind of idea that is just so fundamental to mathematics. This is really the real definition of the limit. So if you're planning on getting a math minor, or you just want to have a little bit of math literacy, this is a good idea to kind of struggle with and get a handle on, and the sooner the better. Okay. But shouldn't come up too much in the homework, if at all. So we've kind of discussed just right now what it means for this sequence to have a limit of 1, right? The limit of this sequence is 1, meaning like eventually my sequence is closer and closer to 1, or infinitely close to 1. Do all sequences have limits? No. A sequence may not have a limit. It may have a limit, may not have a limit. All right, so when does a sequence not have a limit? There's a couple reasons why a sequence might not have a limit, okay? Let's say, I have a line here it doesn't matter where it is, but let's say I have a sequence, and let's plot this sequence, okay? Maybe my sequence is here in blue, and maybe my sequence just keeps bouncing back and forth around this line, okay? It never gets any closer to my white line, right? So this sequence doesn't have a limit, because for that limit to exist, let's say I wanted the limit equal to this white dotted line. Let's say I wanted my limit to equal this. Okay, let's call this L. Well, then eventually my sequence has to be infinitely close to L. It's going to be like right on top of L. Okay, but that's never happening, right? My dots are just kind of bouncing back and forth. So my limit doesn't exist in this case. And I kind of think of this as oscillation, right? Maybe my terms of my sequence are just bouncing back and forth. These are close, but they're never getting any closer, right? So the limit of my sequence doesn't exist. There's another way for the limit of the sequence not to exist. What if my sequence just completely blows up? It just gets huge. Let's say my sequence looks like this. I got dots, and they just keep going up and up and up and up and up, and they just kind of shoot up, boom, go to infinity. That's in that case, the limit doesn't exist, right? There's no finite number that my sequence is going to approach. For any finite number I pick, let's say I pick 100 million way up here, okay? if my behavior stays the same, if my terms just keep growing, well, eventually my sequence is going to be way past 100 million. It's not going to be anywhere close to 100 million, right? So in that case, we have our sequence diverging to infinity or going to infinity. Sometimes when our sequence blows up like that, you might see this notation, limit an equals infinity. And this is a bit misleading because the limit doesn't actually exist here. This notation just we just use this notation to say, okay, our sequence is blowing up, it's getting bigger and bigger and bigger. But really this limit doesn't exist. This is just notation. This is special notation we use when our sequence is going to infinity. Okay. And similarly, our sequence might go to negative infinity as well. So we might see limit of an equals negative infinity. As I maybe let slip a second ago, there's some special terminology for this limit stuff. If a sequence has a finite limit, let's say we have a sequence and that sequence does have a limit L. Okay, for when a sequence has a limit, we say that the sequence is convergent. Okay, and in particular, we can say that the sequence converges to the value L. If the limit does not exist, so if our sequence doesn't have a limit, then we say the sequence is divergent, or that the sequence diverges. Okay. And again, we might want to be specific and say, let's say our sequence diverges to infinity, it blows up. We might specifically say, this is when we might use that notation, limit an equals infinity, or we might say in words, we might say something like sequence diverges to infinity. Okay. So most of this section is going to be about computing limits of sequences. So let me start right off with giving you some useful tool. Well, let's see, I think I'm just going to cover this one. Yeah. So I'm going to introduce you to a very useful tool for computing these limits that kind of goes along with the graphical representation of these sequences we've seen. Okay. So this is in your book. This is theorem 3 in your book. Okay, so chapter 11, you're going to see a lot more of the theorems written out like this. You know, in previous sections, I've just kind of written out maybe formulas or just kind of shown you the process. You're going to start seeing a lot more theorems, really, and you're going to start writing more sentences and stuff like that. So this section of the book is a lot wordier than previous sections. Anyway, diving right into the theorem. If we have a function f of x, okay, and the limit of that function as x goes to infinity equals this number L, okay, and f of n equals a of n, where a of n are these terms of my sequence, then the limit of an as n goes to infinity is also equal to L. So again, this is probably something that doesn't make sense just reading it. What does this mean? Let's say I have a sequence, okay, and I've graphed my sequence, okay. And let's say I know somehow that there's a function that just really, a function of x that really just lies right on top of these points. Okay. Well, then, as you might expect, these things have the same limit. Okay, the limit of my sequence is L, and the limit of, as let's see, should be specific, as n goes to infinity. And the limit of my function equals L as x goes to infinity. Okay, so maybe it's hard to figure out what this limit is, but if I know this function exists and I can figure out what this is, well, then these are the same. So I kind of figure this out by uh, figuring out the limit of my function. Okay, so that's the idea. Usually figuring like, all right, so if you have points, if you have a sequence, okay, what function is lying right on top of those points? Well, it's usually really easy to figure out. Basically what you do is you just replace n's by x's. Okay, so let's see an example. So let's determine whether this sequence has a limit or not. Let's determine whether it converges or diverges, which is going to be most of your problems from this section. So this looks really complicated, right? This is a complicated sequence. I don't really have any good tools yet to work with this. But if I turn this into a function of x, what would that look like? Well, basically what I'm going to do is I'm just going to replace n's with x's. Okay? And I get this. And kind of backtrack, let's backtrack for a second and go back to looking at this. What do you suspect the limit of this thing is as n gets really big? What's happening? Well, the limit of the top is infinity, limit of the bottom would be infinity, right? So we have this kind of infinity over infinity case. You might be thinking two different things. You might be thinking, okay, well that just means the limit of this thing, the limit of this sequence is going to be infinity then, right? I got infinity over infinity. That's infinity, right? Well, no, actually it's not. We don't know what it is. Okay. Then if you recall your Calc 1 a little bit, you might be reminded of L'Hopital's rule, and you might say, hey, this is L'Hopital, this is this infinity over infinity stuff. That's when I use L'Hopital's rule to find the limit, right? So you might be tempted to say, hey, let's just use L'Hopital's rule on this. But L'Hopital's is for differentiable functions, right? In particular, we have f of x, and we can take the derivative and find f prime of x. But this is not a function of x. It's just a sequence. It's just a bunch of isolated points. So this is not a differentiable function. Okay. But this is a sequence, and lying right on top of this sequence is this function. Okay. So basically what I've done is I just replaced my n's with x's. Okay. So this gives me a function, right? This is a function. And then I ask myself, okay, what do I know about this function? What's the limit of that function? Well, just like in my sequence, I have an infinity over infinity, right? As x gets really big, this numerator gets really big, this denominator gets really big. So I got this infinity over infinity case. But now this thing is a differentiable function, so I can use L'Hopital's on it. Okay. So remember what L'Hopital's is. When I have this infinity over infinity case, and I'm trying to find a limit, I can take the derivative of the top and bottom, okay? And then simplify, and whatever that limit is, that's going to be my original thing is going to have the same limit. Okay. So I have this fraction here. I'm going to differentiate the top, differentiate the bottom. Okay, when I do that, I get these. Okay. Check this. This is a little bit of differentiation with a little bit of it's got some chain rule in it. So these derivatives should be fairly basic. Okay. And then just let's simplify the numerator and the denominator separately. I should get 1 over x plus 1 divided by this fraction 1 over x plus 1. So multiply by the reciprocal, and we get this. X over 1 over x plus 1. Excuse me, x plus 1 over x plus 1. So what is the limit of this thing? Well, this term here always equals 1, right? And if you're still not convinced that this limit is equal to 1, we could do L'Hopital's again, right? I could differentiate the top and bottom again. This is, you could kind of say this is infinity over infinity again. So I do L'Hopital's again, and what do I get? I get 1 over 1 when I differentiate again. Okay, and then this is just equal to 1. All right. So my limit of my function of x is 1. So what have I found out? I have found out that the limit as x approaches infinity of ln of 2x plus 2 over ln of 3x plus 3, I know this limit equals 1. By my theorem 3, I get this conclusion, that limit of ln of 2 plus 2 over ln of 3 plus 3 as n goes to infinity is also going to be equal to 1. So a little bit of a complicated tool, but very useful, and that will come up on the homework. I'm gonna do one more little tidbit, and then I'm gonna break this video up. I'm gonna I'm gonna end the video in just a minute. This is a really long section. It's one of the longest sections in our course, so this is going to be 2 videos. Before we end, though, let's talk about limit laws. So these are just really straightforward guidelines, and yeah, that is the last thing. These are really straightforward rules when we have convergent sequences. Okay, and you've probably seen something very similar to this in Calc 1 before. Okay, but this is specifically for sequences, but it's very similar to what you've seen before. Okay, so let's assume AN and BN are 2 convergent sequences. This convergent is really important. This way of splitting up limits only works if these limits are convergent, right? And let's assume C is just a constant. Okay, we have these nice rules or laws. If I take the limit of AN plus BN or limit of AN minus BN, that's just going to be the sums of the limits. Okay, it's the limit of AN plus limit of BN. So for example, what's an example of what do all these rules mean? Let's say I have limit of 1 over n plus 3 over n. No, let's do something different. Limit of 1 over n plus about 3 over 1 plus 1 over n. Okay. What is this limit? Okay. Maybe this is kind of complicated to do together, but using if I know these are convergent, I can split it up. So let's look at these terms individually. Let's look at this thing. What's the limit of 1 over n? Think about it. As n gets really big, what's happening to this fraction? Let's say n is 100, then I have 1 over 100. What if n's 1,000? Then I have 1 over 1,000. It's getting smaller and smaller and smaller. So this limit is 0. Okay, so this sequence is convergent and converges to 0. What about 3 over 1 plus 1 over n? What's the limit of this? Well, let's see. My n is right there, right? So as n gets bigger, this is the same thing as what we had up here. As n gets bigger, this term is going to 0. And I should just be left with 3 over 1, which is 3. Okay. So this limit's equal to 3. So I know both of these pieces are convergent, right? These sequences are convergent. So I can use my limit laws to say this is equal to limit of 1 over n plus limit of 3 over 1 plus 1 over n. Now I can consider these things individually. I know this first limit is 0. I know this second limit is 3. Okay. So this is how we apply that law or that rule. Okay, we did it for addition, but it also holds for subtraction, which is why I have the plus minus here. Okay. If I have a constant times a sequence, I can bring, and let's see, I know this an is convergent. Okay, I can bring this constant c outside my limit. That's essentially what's going on here. So the limit of c times an is equal to c times the limit of an. Okay. So another example, okay, let's say I had a limit of 3 1 plus 1 over n. Okay. Let's say I'm considering this limit. Okay. Well, I got a constant here, right? So I pull that constant out. Okay. So that's equal to 3 times the limit of 1 plus 1 over n. And then what's the limit of this thing? Well, this term is going to 0. This term's constant. So it's 3 times 1, 3. I have another 2 more results. Okay, if an and bn are convergent, the limit of an times bn is equal to the limit of an times the limit of bn. Okay. And then finally, we have the same thing with division. As long as the limit of this bn is not equal to 0, right? If this limit on the bottom is 0, then this is like 5 over 0 or something like that. That's not defined. So we need to always be sure that limit of bn is not equal to 0. Okay. And that's it for the limit laws. So again, this is a very long section, so I'm going to stop here and do cut part 1 off here, and then I'll pick up where I left off in the next video.